Lab 4. So the purpose of this lab was to predict behavior of resistors and capacitors and find the electric potential energy difference between parts of a circuit. The useful formulas included the loop rule, Ohm's law in the form I equals V over R, change in voltage of a capacitor plus change in voltage of a resistor equals 0, and change in voltage equals initial voltage times e raised to the negative of time over RC, and the results were that my predicted RC and actual RC of the circuit didn't line up. The setup for the DC circuit, 2 batteries hooked to an ammeter, hooked to 2 different resistors, hooked back to the ammeter, and then hooked back to the battery. And for the RC circuit, if we don't include the battery used to charge it, it's a capacitor hooked to a light bulb that acts as a resistor, hooked back to a capacitor. So for the DC circuit, my initial current prediction was 3 volts over 147 ohms to get 0.0204 amps, which was about right. And I used the voltmeter to look at electric potential differences. Where one of the ammeters was, I got -3. That's the potential drop from the resistance. And the other ammeter read 0 volts because the voltmeter doesn't provide an alternate path, so current is none. For each of the electric potentials at different parts of the circuit, the batteries add 3 volts to the electric potential. The wires have no resistance, so they don't do anything. The first resistor drops potential by 0.96 volts and the second by 2.04 volts. And we can see that over here in the graph, where each battery is adding 1.5 volts to the electric potential, and each resistor is stepping it back down to 0. And when we're using the voltmeter, it only measures potential. It doesn't provide an alternate current path, so the ammeters read the same current the whole way through. And then over where we provide an alternate path with an ammeter, the other ammeter after the resistors reads 0.06 because the current will flow through that ammeter instead of through the resistor. And these ammeters don't have resistance on them. So for the resistance of each of the resistors, the first one has a resistance 48, the second of 102. So for the RC circuit, the light's behavior is that it'll start up and fade out as the capacitor charges. Once it's fully charged, it blocks the current. And once we hook the capacitor up to the light will turn back on and fade out as the capacitor loses charge. And over here we can see the time it takes for the capacitor to charge and discharge with a 10 ohm light and a 20 ohm light. Here's my prediction for the RC value with a initial voltage of 9, a change in voltage of 8.68. So natural log of 8.68 over 9 equals -20 over RC, and the RC was 552. These are the times that went into this graph here, and this slope would produce an RC value up here, and they don't line up because that's -1.66x. So the model versus reality. Wires have some resistance in reality, so they would affect the current. And then chemical batteries, which we're modeling with, don't transfer 100% of their potential all the time. There are certain other types that do. And then errors on the RC value, timing issues for one, and then there was certainly a serious error somewhere in my actual calculation for my prediction. And then the what if questions. For the ammeter question, ammeters use shunt resistors to divert current to them, so the ammeters in the circuits would act as resistors in reality, and the current in the circuit would drop as more ammeters are added. And then for the other one, the ideal model predicts a short if a battery is just hooked to a capacitor, as there is no initial resistance in the capacitor. This may happen in real life as well, unless the wire has enough resistance to the charge, or the capacitor is introduced partially full so that can act as a resistor.